we're going to deal with two very important topics: an exploding star and the latest probe to the moon. But first of all, our news notes with Chris and with John Mason. John, I know you're just back from Prague, where the International Astronomical Union had been meeting, and the committee which I was a member 2 years ago was discussing the status of Pluto. Is Pluto a planet? Well, it was pretty heated, I gather.
It was. I think it's probably one of the most intense debates I've ever seen at the IAU, and I think because people passionately care about whether Pluto is a planet or not. And of course it will come as a surprise to many people, I'm sure, that until this particular meeting we never had an official definition of what a planet was.
No, we haven't.
We didn't need one.
Nope.
It wasn't until the discovery of Xena 2003 UB313, beyond Pluto, and of course which is slightly larger than Pluto, that the debate really heated up. And the debate has centred about what actually constitutes a planet. And there have been a whole number of proposals. What they've come up with, to most people, will sound as a very complex proposal indeed. They've basically proposed dividing the solar system objects into three: planets, dwarf planets, and small solar system bodies. Now, the definition of a planet is it will be in an independent orbit round the Sun. It will be massive enough to have enough gravity to have pulled itself into a nearly spherical shape, although quite how spherical is open to debate. And the third criterion is that it must have swept its orbit clear of other material, the neighbourhood of the planet around its orbit, swept it clear. Those three criteria, if they're fulfilled, then it will be called a planet. And there are 8 bodies that satisfy that criterion. They are Mercury, Venus, Earth and Mars, Jupiter, Saturn, Uranus and Neptune, the so-called classical planets.
Exactly, yes.
Now, dwarf planet is an independent orbit round the Sun. It's large enough to have pulled itself into a nearly spherical shape, but it has not swept the neighbourhood of its orbit clear, and it isn't a moon or a satellite of a planet. And there are at least 3 objects that fit that category. There's Ceres, the largest asteroid, there's Pluto itself, and there's Xena, 2003 UB313. But there could be many more. There may be dozens of other objects that fit these criteria waiting out in the wings. And the third criteria, small solar system body, is for everything else.
Well, it makes no sense to me at all. Where does the dividing line come to start with?
Well, the IAU are going to set up a number of committees to look at objects that are near the dividing line between the categories. I don't think we're going to have perhaps much argument about the 8 major planets.
No.
Where we are perhaps going to have an argument is about whether an object is a dwarf planet or a small solar system body. And of course there are so many new objects being discovered beyond Neptune. I'm sure many of those trans-Neptunian objects will become dwarf planets. And there are certain asteroids which could all be considered as dwarf planets if they fulfil the criteria.
What about Pluto?
Pluto is a dwarf planet and not a major planet, but that's no real surprise because for most of us, certainly myself, I've not really considered Pluto a major planet for a long time.
It wasn't.
To me, it was a Kuiper Belt object, a trans-Neptunian object, and was never really a proper planet.
Well, I think I might make a comment here, because after all, Clyde Tombaugh, who discovered Pluto, was a friend of mine. He asked me to co-author his book when it was I did, so I think I'm entitled to say something. It strikes me, this is all very complicated. I think it should be simple. We have the 8 classical planets and everything else are classified as planetoids.
It may well be that, despite what the IAU says, ordinary people may well continue to do what they have done for many, many years.
Well, in my view, if these complicated rules go through, in a few years, no one's going to take the slightest notice.
You could be right.
Well, I wonder what will happen, John. Well, what do you think about it, Chris?
Well, I think I'm with you, Patrick. And maybe we should talk about something we know is a planet, and that's Mars.
And there are interesting things there. These curious dark spots that appear near the Martian South Pole quite regularly.
That's right, and somebody's finally come up with an explanation for these features, and it's quite startling. At the Martian poles, you have a permanent ice cap, mainly water ice, and then during the Martian winter, that gets covered up with a layer of carbon dioxide ice.
Exactly.
Now, what we think happens is radiation is able to penetrate through the carbon dioxide ice, heat, dust trapped between the layers. That heating sublimates the ice, turns it into gas.
And they're a geyser.
Exactly. Pressure builds up, and you get these incredible geysers, which pull up material, pull up carbon dioxide, but also the sand and grit,
Indeed.
and deposit these black spots on the ice. So it's probably a tourist attraction of the future.
I'm sure it is.
Must be a
That activity
spectacular
there.
sight.
And don't forget also, the two rovers, Spirit and Opportunity, are still going strong.
That's right. Remember, these rovers were supposed to last 90 days on the surface, and they've just survived their second Martian midwinter, effectively. So it looks like, with any luck, they'll keep going for the next few months. Now, something will eventually go wrong.
Good orbiters too.
That's right. There's a whole fleet of spacecraft looking at Mars, and every month we end up talking about all these wonderful new results from the planet.
And is there life there? We must wait and see.
We're working on it.
Now let's go further out, to your province. What about the new results on dark matter?
Now, this is an interesting one. Remember, we've believed for a long time that most of the matter in the universe is of a mysterious kind, what we call dark matter. Not ordinary atoms, but some mysterious heavy particles. Now, we're beginning to get a sense over the last few years of how it behaves. We still haven't detected those particles directly, but we can see their effect. Take this for an example. This is an image of the bullet cluster.
Yeah.
Now, the pink in this image is an X-ray image of the cluster, so it shows the hot gas. And within that are lots of different galaxies. But we just look at the gas because that pervades the entire cluster. Now, by looking at the background galaxies, we can see how their light is bent by the presence of the bullet cluster. And that gives us an idea of where the mass is. And that's shown in blue in this picture. Now, what you see is that the pink is much more concentrated towards the centre. This cluster formed, as we can see in this animation, when two larger clusters passed through each other. Now, as they do this, the normal matter feels a resistance, kind of like air resistance, but a pressure on itself. Dark matter only interacts via gravity, and so sails on much further out. And that's why we have this separation between the mass, mostly dark matter, and the baryons, the gas sitting in the middle of the cluster. And it's difficult to see how you'd explain this without a huge amount of dark matter in the cluster.
Do you believe in dark matter, John?
I do believe in dark matter, yes I do, and I think that it's incredible that these observations reveal the presence of dark matter in these distant clusters. It's marvellous.
I think the point is we're beginning to get we still can't I can't put my finger on a dark matter particle, but we're beginning to get an understanding of the physics of it. How does it behave in this sort of situation?
What else in your field?
Well, there's been some marvellous results about star formation. For starters, this wonderful picture of a star-forming region in the Large Magellanic Cloud, a dwarf galaxy orbiting the Milky Way, taken with the Hubble Wide Field cameras. Beautiful image. And what about this image from Spitzer of the most famous of all star-forming regions, M42, the Orion Nebula? Now, it's not just a beautiful image. If you zoom in on the newly forming stars in this image, Spitzer's been able to discover over 2,000 of these newly forming stars surrounded by protoplanetary disks. Disks that will go on, we think, to form solar systems. And it turns out that 60 to 70% of the stars forming in the Orion Nebula right now have these disks. So that raises two questions. One, it tells us something about how common planets elsewhere beyond our own solar system must be, but it also raises the question of what happened to the other 30%. Why don't they have disks? Which stars do end up with them? And that's a question that images like this will enable us to investigate much further.
So there's plenty going on. And earlier this morning, a lunar mission came to the end. That was the Smart 1 probe. And I talked about it to one of the project scientists, Professor Bernard Fong. First of all, can you tell us a bit about Smart 1? It's not the usual rocket probe.
No, Smart 1 is a new type of spacecraft making use of a revolutionary engine, an ion engine that will allow us to go deep in interplanetary space. It is using only solar power to create electric charges that are expelled at high speed from the spacecraft. And with this, with a gentle thrust applied for months and months, we could go from the Earth to the Moon.
How long did it take to get there?
Well, we broke a Guinness Book of Records, 13.5 months, the slowest mission to the Moon. But as well, we used the smallest amount of fuel, 60 liters.
Well, the probe has been going round the Moon now for a long time.
Yes, okay. We arrived in November 2004 in capture, and we used the ion engine again to spiral down and down to a distance from 300 to 3,000 kilometers around the Moon. And so last year in September 2005, we would hit the Moon if we would not have done a special maneuver to reboot the orbit and extend the mission by 1 year. but for this we use our last drop of fuel. And then immediately we were to impact the moon. And we would have impacted the far side of the moon if we would not have used a little trick that we came up with our engineers to make use of the thruster used to orient the spacecraft, also to move the date of impact where it will be visible from the near side of the moon.
Did you choose that area particularly, the Lake of Excellence, not far from the great crater Shepard?
It's a very interesting area. This is a volcanic plain surrounded by some ancient islands. And so it's a type of terrain which has not been sampled by the other mission before. So in a sense, we are going to scoop this area, and we try to eventually measure also some of the signature of the ejecta produced by this soft impact.
One rather interesting aside, you've covered the entire moon, and near the North Pole there are two mountains that are always illuminated, the mountains of eternal night.
Yes, indeed, the axis of rotation is perpendicular to the sunlight, so there are some areas near the poles where we have found on the rim of the crater, over the winter nights, there is always sunlight. And we have monitored this tiny area, a kilometer square. This would be very good places to have a robotic outpost that would use only sun power and would last for a long time.
What about some of the landing sites?
Yeah, we have observed some of the Apollo and Lunar landing sites, first to calibrate our instrument and to try to bridge between the ground truth from this landing site with orbital truth, which is more global. And in particular, we have mapped the Apollo 15 lava tubes. It's 120 kilometers long and 1 kilometer wide lava tubes, and for which we have compared our data with some of the panoramic landscape taken by the Apollo 15 lander. And clearly we can check that these are consistent, and we can build from this knowledge to better also know other places on the surface of the moon.
What about the Apollo 11 landing site where Armstrong and Aldrin came down?
It's one of the safest landing sites, and it has almost no feature. And we can use that to compare with previous observations and to merge our data with data from previous missions or from the ground.
Of course, the base of the Apollo 11 rocket is still there, but you couldn't see that.
We have not had the resolution to detect the artifacts proper, but in the last phase of the missions, when the sun is in a very grazing angles, we observed some of this site to see if we would be able to detect some very long shadows cast by some of these artifacts. We are still analyzing the data.
Well, you know, people are still asking, when are men going to go back to the moon? What's your guess?
My guess is now we are in a phase which we call the International Lunar Decade, where there will be robotic infrastructure in orbit, and then our project, the goal is to have some landers that could form a robotic village. And then after this, from 2017, we expect to have human returning. But thanks to this robotic precursor, we can do that in a cost-effective manner, and also in a way where we could attain a sustained settlement and a permanent presence.
Well, Smart 1 has now come to the end of its career, but you've been outstandingly successful. It's told us a great deal, and we are very grateful that you've come along to tell us about it. Bernard, thank you very much.
Thank you very much, and I hope that Smart 1 also inspires the next generation of explorers and innovators, and that are going to build also the next missions to explore the solar system.
It's one small step for man, one giant leap for mankind. There is orange soil. Well, don't move it till I see it. It's all over. 2, 1, ignition. Right away, Houston.
So the moon is very much back in the news, and so is the sun. 2 new solar probes are being prepared and will be launched in the near future. Chris has been investigating.
The last decade or so has seen the launch of a whole flotilla of spacecraft to study the sun, all sending data and images down to dishes like this one at the Rutherford Appleton Laboratory in Oxfordshire. The latest to join the fleet is Stereo. Due to be launched in the next few weeks is not one probe, but 2 identical twins which will separate after launch and go their different ways. A UK team at the University of Birmingham and here at RAL have been involved, contributing to several of the instruments aboard this NASA mission.
Stereo, I see it as leaving the cradle. all missions that have imaged the sun, looked at the sun's disk, have done it from near the Earth, or on the Earth if you like, or just in front of the Earth in the case of SOHO. What we've never done is get away from the Earth and look at the sun's disk. Stereo is basically two spacecraft that will head out sideways, move away from the Earth with time. And the idea of that is that you can look back at the sun from two angles. If you do that, you can make a stereo view of the sun. You can see the sun in 3 dimensions. And if you think of that complex atmosphere, that complex spaghetti-like atmosphere that you see in 3 dimensions, you can really begin to piece together what really is happening in there. It's going to be complicated, but it'll look fantastic. A real thing to work on to understand how stars work. But the other thing is, if you're looking from the side, you can see what's coming our way. You can see the Earth and the sun, if you like, effectively at the same time, and see the clouds coming towards the Earth and predict when they're going to arrive. It's a real sort of space weather mission in that sense. And with the 2 spacecraft, you can see the shapes of those clouds, how they evolve, and predict what they're going to do when they get here. What's the technological challenges in looking at those clouds heading our way? The real challenge, I think, is that the 2 instruments bolted on the side of those spacecraft, those are called the heliospheric imagers, which are the British-led instruments, are basically looking at deep space, sideways from the sun. They're not looking at the sun, they're looking sideways. And you're trying to see these clouds go through space, and they're going to be very, very weak. You're going to be detecting stars all over the place, of course, down to 13th magnitude or whatever. You're going to see the zodiacal light, the so-called F corona. You're going to see scattered light, of course, in all instruments you do. And you're going to have these weak clouds travelling through as well, and you've got to pick out the signals of those. It's a real challenge. So the instruments are basically little telescopes which are mounted deep inside if you like, a box full of baffles, which take away all the scattered light that you could possibly imagine or model. So it's as dark as possible to try to detect these things.
The largest of these eruptions from the sun's surface, and those that have the largest effect here on Earth, are known as coronal mass ejections, seen here in images from the SOHO spacecraft, which has spent more than 10 years staring at the sun. In these coronagraph images, the sun's disk has been blocked out, creating an artificial eclipse, allowing us to see the sun's outer atmosphere.
A coronal mass ejection is an enormous explosion of hot gas from the surface of the sun, something like 1,000 million tonnes of material coming off from the surface of the sun at enormous temperatures, millions of degrees. And those travel out into space, and what we're interested in is when those clouds come towards the Earth, because the Earth is a quite small target in space really, but we're living on it, and we will have to deal with the consequences of one of these clouds coming past. And the consequences can be spectacular. Well, the most wonderful thing about these coronal mass ejections is they create the northern lights, the aurora, beautiful lights in the sky. The Earth's magnetic field concentrates the gas particles to the north and south poles. They fall into the atmosphere there and cause the air there to glow, very much like a neon tube in a house. But there is a more serious side, because this is quite high energy plasma in space, this gas that's come away from the sun. And it's that can cause damage to spacecraft. And of course, with 2 cameras on 2 spacecraft, you can actually map the evolution of the CMEs in 3D. Well, you can see from some of the observations we've got of the coronal mass ejections on the surface of the sun that the features that they emerge from are very complex. There's lots of magnetic field lines that are distorted and twisted. And while we've got excellent views of these from SOHO, when these things are moving and twisting, it's very difficult to work out how those features actually map onto each other. But with 2 cameras, we can have a 3-dimensional view of that and actually reconstruct that in 3 dimensions, which is going to be an enormous help in working out how these things evolve and what causes them to be triggered and send material out into space. It's a busy and exciting month for solar astronomers, with the launch not just of Stereo, but of the Japanese-led mission Solar B, which also has substantial involvement from both British and American astronomers. This mission will look at the active surface of the sun in the extreme ultraviolet region of the spectrum.
This is a structural model of the ICE instrument on board the Solar B mission. ICE stands for the Extreme Ultraviolet Imaging Spectrometer, and Solar B is a Japanese, UK, US mission to study the sun, the active sun.
And how does the instrument work? The light comes in, what, up here?
The light comes in up here, yeah. What you don't have here is the last part of the light baffle, which protects from any stray light. Comes down to this end, which reflected off the primary mirror, then it goes up to the top end, which reflected off a grating, and finally comes down to this part here, where we have the 2 CCD detectors.
But why the extreme ultraviolet?
Well, the extreme ultraviolet is an interesting region of the spectrum. It emits from the area which above what we think of as the surface. We have the surface which you see on a sunny day in this country, which is the photosphere. Then it's surrounded by a thin layer called the chromosphere, which you only normally see during an eclipse, very, very briefly. But the solar corona, which we're used to seeing in sort of very white streaky light from eclipse pictures.
The pearly white bits.
Exactly. Tends to emit mostly in the X-rays and extreme ultraviolet region. And that's where we see most of the interesting stuff that happens day to day on the sun. In areas above sunspots, in active regions, the gas emits very, very strongly at extreme ultraviolet wavelengths. And we also see things, apart from the active regions, we think things like coronal holes, polar plumes, helmet streamers, all the things that vary on hour-to-hour and day-to-day time scales, which you don't necessarily see quite so easily on the surface.
The launch of SOHO a decade ago completely revolutionised the way we view the Sun, and the launch of these 2 new satellites will do the same. Astronomers will be able to monitor the active surface of the Sun and, for the first time, directly observe its effect on the environment around it. That will help reveal the secrets not just of the Sun itself, our nearest star, but also of all stars. After all, only one is close enough to be studied in such fantastic and beautiful detail.
Our Sun is a steady, well-behaved star, but others are not. And one of these is called RS Oph in the constellation of the Serpent Bearer. Normally it's faint, but recently it flared up to naked eye visibility. It is causing great excitement among astronomers. And I'm joined now by Professor Mike Bode of Liverpool John Moores University and Dr. Tim O'Brien of Jodrell Bank. Welcome to the Sky at Night. First of all, Mike, what exactly is RS Oph and why is it so exciting?
Well, RS Oph is what's known as a recurrent nova. We've actually observed, prior to the current outburst, 5 well-observed outbursts between 1898 and 1985, which is the time of the last outburst.
So it's all that flares up periodically, then?
Yeah, absolutely, yeah. Every 10, 20 years or so, it has this major outburst.
Why?
Well, we know that RS Oph comprises 2 stars, which are relatively close together. One of these stars is called a white dwarf. It's about the size of the Earth, containing, we think, something over the mass of the Sun in what is relatively a small volume. And this is in orbit with a red giant star, a star much larger than the Sun. And the 2 stars are going around each other in about just over 450 days.
How far apart are they?
Well, there's somewhat larger separation than the distance from the Earth to the Sun, say a couple of times that distance, but they are relatively close together, considering one of them is a red giant.
So look at the telescope and they'll appear as one?
Absolutely. You can't resolve the 2 stars normally. But what we have in this system is a transfer of material from the red giant star to the white dwarf. And this hydrogen-rich material builds up over a period of those 10 or 20 years to the point where you get a nuclear explosion occurring in the bottom of this envelope. And that throws the envelope off into space at thousands of kilometers per second. Now, in this system, the red giant is losing material in a wind. And when the explosion occurs and this mass of material, which is about a millionth the mass of the Sun, flies out into the red giant wind, it slams into the wind and sets up shock systems. And it's the emission from those shocks that we've observed both in X-rays and in the radio, and has made this a really exciting event for us to follow.
How far away is it from the Earth?
We think it's about 5,000 light years away from the Earth, actually, so it's relatively close by in astronomical terms. It's well within the Milky Way galaxy.
What happened recently?
On Monday morning, in fact, on 13th of February, an announcement was made that some Japanese astronomers during the evening of February the 12th had spotted that it had exploded again for the first time since 1985. So we were quick off the mark, we were prepared for this, and we used X-ray satellites and radio telescopes, many different observatories across the world, in fact, to follow this explosion in detail since February.
And what's happened since then?
Well, what happened was on the Monday morning, as Tim says, we alerted these facilities, and by the Wednesday, we'd actually got X-ray observations from the SWIFT satellite showing that we had a bright X-ray source. 36 hours later, we observed it again. It was even brighter. But the X-ray emission was telling us that the temperature of the gas that we were seeing was actually decreasing with time. And that's consistent with shocks that are flowing through this red giant wind, gradually slowing down and getting cooler. And we continue to follow the outburst with Swift, and we still do now, but with the first month we saw evidence of these shocks spreading out through the wind in just the same sort of way that you see a supernova remnant evolving, but we were seeing it on weeks and months timescales instead of hundreds or even thousands of years timescales.
What did they will happen next?
Very quickly, use the VLBA, which is the American Very Long Baseline Array, which is spread between Hawaii and the Caribbean, to image this in radio waves, and we saw the shockwave itself surrounding the binary system. We can actually see the ring of emission from what we believe are electrons, which are accelerated in the shockwave to very high speeds, and they generate this radio emission that we could see in the images. And over the course of the next few weeks, we observed it again the following week, with the European VLBI network, which is a network of radio telescopes spread all the way across Europe, and in fact including telescopes in China and in South Africa. And we could see this shockwave expanding, and from that we can actually directly measure the speed, and the speed turns out to be about 4 million miles an hour.
Quite big.
So it's it's moving quite fast.
Yeah.
Well, there aren't very many of these recurrent novae. What does my going to tell you ultimately?
What we eventually want to determine is whether the white dwarf in this system, which we suspect is near the maximum mass that a white dwarf can have, beyond which it will explode as a supernova, we want to determine whether more mass is being added to the white dwarf and therefore moving it nearer and nearer to that limit with time, or whether it's actually decreasing in mass. It actually loses more mass than it gains at each outburst. And that will be very important, because then we will have a system that we will have that's relatively close by, that we can see in great detail, that is what's called a supernova progenitor system. The other thing that we're learning about here is, as I said before, we're seeing effectively a supernova remnant as the shocks spread out through that wind, but in miniature. Yeah. And it's evolving very, very rapidly. And the same sort of processes that go on in supernova remnants are occurring in this object.
So presumably you'll go on studying it in all wavelengths?
Yes.
Yeah, it's settling down now. It's fading away, both in the visible. It's down to 11th magnitude now, so it's no longer a naked eye object. In the radio it's fading away, in the X-rays it's fading away. But what we're hoping now is to see it sort of get back into the same state that it was before this most recent explosion, and it's not quite at that level yet. So to understand the story fully, we need to follow it right back to its so-called quiescent state.
And amateurs can help here.
Indeed, amateurs can help here. I mean, what we're seeing now is a brightening that's about magnitude 12. Yeah. We expect it to go back up to maybe magnitude 11, 11.5 or so. And amateurs can certainly do those observations and put points on that light curve to help us sort of look for the signature of this accretion process.
And then we'll know more or less what's going to happen, we hope.
Yes. We hope so.
Yeah.
Mike, Tim, thank you very much. And when I come back next month, I'll be talking about the autumn sky. Believe me, there's plenty there to see. Until then, good night.